The purpose of this lab is to observe a magnet falling through an aluminum tube, comparing these observations to a computational model. To do this, we will need to consider Faraday's law, the Biot-Savart law, Newton's second and third law, and Ohm's law. We found that the model predicted the magnet to fall faster than the magnet actually fell. In this experiment, we will be considering a magnet in an aluminum tube as the system for this experiment. The magnet was dropped with the north side down 5 times. The amount of time that it took for the magnet to fall was recorded. We assumed that air resistance was negligible and that gravitational and magnetic forces were the only forces acting on the magnet. These are the physical observations of the experiment, including the tube dimensions, magnet properties, and average fall times across the 5 drops. Here's the code used to predict the falling of the magnet. We modeled the tube as a bunch of infinitely small rings stacked on each other. This made it easier to calculate the magnetic force on the magnet, so we know how rings produce magnetic fields. First, we input physical constants. Then we create the function to model the tube as rings. Then we calculate the magnetic force produced by the magnet and then the flux through the tube. We then compute the net force from gravity and magnetic force to determine the magnet speed. The model outputs a visual showing the magnet fall. It also produces this graph of velocity. Based on the model output, the magnet fell faster in the model than in what we actually observed. This means that the actual magnet had a greater magnetic force acting on it. It is possible that the mu used for this experiment, for experiment 3, was incorrect, or that the aluminum was thicker than we had assumed, both of which could lead to an increase in the magnetic force. If the resistivity of the conductor were 0, the magnet would fall slower due to a higher current and higher force. If holes were cut in the tube, the magnet would fall faster due to a lower or disrupted current. All right, that's it.